Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education.
Hello, Senior 4 Chemistry students. Welcome back. Alan is my name, still with you in chemistry. I hope you're fine. So we are now heading into a different unit, and that is Unit 16, which is about acids and bases. And the subtopic, it is under the topic of ionic equilibrium. We finished up Unit 15, which is about factors affecting chemical equilibrium. Now we are looking at ionic equilibrium. The whole overall topic, it's ionic equilibrium. If you happen to look for it on internet or on other sources of information. So we are looking at acids and bases, and in this case, it's going to be a single unit or a single lesson covering the whole of this unit. And we're going to look at definitions of acids and bases, that is basing on different theories. Then we look at the definition or the explanation of the acid-base conjugate pair. We look at the classification of acids basing on their strength, either weak or strong acids. And as usual, I always highlight the key terms for you not to miss. In this lesson, we're having about 4. One is hydrozonium ion. This actually it has many names or many terms, as you're going to see them. You can call it a proton, you can call it a hydrogen ion, you can call it hydronium ion, you can call it ozonium ion, you can call it hydrozonium ion. So I'm bringing you those terms. If we use them, do not wonder and ask yourself, what is that? They are used synonymously. So a proton or the hydrogen ion is when a hydrogen atom loses an electron. Then it forms a hydrogen ion, simple. So then we have hydroxide ion as a new term, or as a key term we shall use. Then we have alkalis. Basically, when we talk of bases, you can have insoluble bases or soluble bases. If the base can dissolve in water, then that is called an alkali. Then we end up with acid-base conjugate pairs. These are the key terms we shall continuously be using. And this takes me to objectives. You should be able, by the end of this lesson, to write appropriate equations to illustrate. Not only writing, but your equations should illustrate the different definitions of acids and bases. Then you're supposed to identify the acid-base conjugate pair in any acid-base reaction. Meaning you need to be knowing what is a conjugate pair. And that is what we shall look at. Do not miss, please. Pay close attention. Let's get started. Have a look at that image. What do we see? What do we see? Some of us enjoy taking a cold Pepsi, don't we? Yes, we do. Others enjoy taking lemon in their tea. To the girls and some of us who like cooking, we enjoy using apple cider vinegar in maintaining our salad. So you notice, some enjoy wine, but of course you students, you're still young. A majority of you are still below age of 18, so you're not supposed to be taking alcohol, and wine is a part of it. So what do we notice? These are the compounds that are within our reach. We are in every day interacting with these components. The lemon, the Pepsi drinks, and so on. So, did you know that these components actually contain acids? Yes, they do. These are acidic substances that we are that we encounter in our day-to-day lives. Take a look at the wine coming from the grapes. They have acids, and specifically it is tartaric acid. Majority of us enjoy taking chivuguto, sour milk. That chivuguto is having lactic acid. It is the reason why it brings in that sour component. The lemon you take, at least almost all of us know lemon. It has citric acid. Some people who like going into sports in their jogging as they pass through forests, there are these ants. They smell. Their smell is because of formic acid. Of course, I can't talk of vinegar. You know vinegar, that is acetic acid. So you notice we are surrounded by acids. When we talk of acids, do not think of the sulfuric acid in the lab. Even these are acids. They have acid component. And what is very unique with the acids is that sour taste. That tingling when you're eating that lemon and that tingling part or feeling that you get. You see the illustration in here. That is the sour part of acids. So when we're looking at acids and bases, do not only look at the sulfuric in the lab or other bases in the lab. No, in our day-to-day lives. Take another look at this image. Don't we use Windex in cleaning the windows, the glasses on our windows, and even tables which are made up of glasses? That's Windex. We eat bread. In making bread, they use baking soda. We take a shower in evenings. What do we notice? We're using dual soap. We wash our clothes and everything using Omo and sunlight. Remove this, go to the lab, you'll find sodium hydroxide. Did you know that these components are actually basic? Yes, they are. The Windex is ammonia. Baking soda is sodium hydrogen carbonate. The dual soap you use has potassium hydroxide, which gives it that soft aspect that when you use, you feel your body is very soft. So we are actually surrounded by acids and bases. Now I ask, what is an acid and what is a base? What is an acid and what is a base? I'm wondering, I want you to give me the answer. What is an acid and what is a base? I'm waiting to hear from you. Give me the answer. You're right. I'm pretty sure you have a thought. But let's continue and see what is exactly an acid. So acids and bases were defined differently by different people, and so there came the aspect of acid-base theories. So we're going to be looking at these different definitions and who defined them. Let's get started with the first scholar. In 1880, that is way, way many years ago, about a century and so on, these two scientists, Oswald and Arrhenius, came up with a definition. For them, any substance which, when dissolved in water, can produce a proton, can produce a hydrogen ion, is an acid. HCl, for instance, is an acid because it has hydrogen which can be released in water. We're bringing in water in form of aqueous, you know that. Then to them, a base is a base if it can release OH ions in water. Sodium hydroxide is a base because it releases OH ions. So, to them they summarized and said, an acid should release hydrogen ions and a base release OH ions. Simply releasing, donating, or producing. They did not put other more terms. And to them, they finally said, a base should be an alkali. In other words, should dissolve in water. Any base which dissolves in water is termed as an alkali, and to them, a base should be soluble in water. If you have any base which is not soluble, to them it's not considered as a base. That is the first part. These are the fathers of acids and base theory. When they finished, then we can bring in the aspect of hydronium or the proton. I want you to take note of this. Remember, we brought this as a key term. I want you to know it because we're going to be using it. Now, hydrogen ion exists because it has lost an electron. And because it is only having a single proton, that's why it is called a proton. Being a proton on the ion of hydrogen, it exerts a high charge density, +1 over the size of hydrogen ion, which is around 0.00 something. So you end up having a unit 1. Being highly charged, it attracts the lone pairs of oxygen in the water. Remember, it is existing when it is in solution. As it attracts the lone pairs of electrons on oxygen in water, it forms this compound, or which we call ozonium ion. Oxygen has donated the lone pairs to hydrogen, and so the positive charge which was residing on hydrogen is now residing on oxygen, which is the central atom, and it is bigger in size. So this becomes a stable molecule in water. The bonding is called coordinate bonding. We've looked at that in the bonding. So this is where the 4 names come about: hydrogen ion, a proton, because it is simply made up of 1 proton in the nucleus, hydronium ion or hydrozonium ion, because it is coming from this molecule ozonium, oxygen ion, H3O positive. So if we use this structure, or we use hydrogen ions, exactly we are meaning this molecule, hydronium ion. That is the one key term defined now. So when we're talking of hydronium ion, ozonium ion, hydrogen ion, we are synonymously implying to this structure. So let's now look at the second definition of acids and bases. Remember, Arrhenius and Ostwald, they said an acid simply releases hydrogen ions. A base simply releases OH ions. They didn't put other more terms. And remember, we are surrounded by acids and bases as we started at. So Bronsted and Rode, they came in 1923, just a few years when Arrhenius had defined. For this, they modified Arrhenius' definition by saying, an acid should be an acid in the presence of a base. The base to take up the hydrogen ion which has been released. For instance, HCl will be an acid only in the presence of a base which is water. When you dissolve it in water, it forms the hydronium ion. So in this case, it acts as an acid. Hydrogen sulfate is also an acid because there is water as a base. So to them, an acid will be an acid in presence of a base. Similarly, a base will be a base in the presence of the acid to donate a proton. In other words, if you have ammonia, for instance, it will be considered as a base if it can accept a proton from an acid, in this case, water. And that's why in Windex we say this component is basic because the ammonia is dissolved in water to form the solution. So in that way, it is considered as basic because it is the interaction of the base with water as an acid. Or bring your chloride, remember this? The chloride will be a base, to Bronsted and Rode definition, in presence of anything that can donate a proton. Bring this equation and bring it here. At start, this was the aspect. Here we have the chloride taking up a proton to form HCl and water. This is a base, this is acting as an acid. So, what do you see? To the Bronsted-Rode definition, one can be an acid, at the same time it rotates and becomes a base. depending, there should be a proton, no, there should be a base for an acid to exist, and the base will exist only if there is a proton to accept. So this is where we have the third key term, acid-base conjugate pair. Acid-base conjugate pair. What do we mean? Let's take a close look at these structures. Water is an acid in presence of ammonia because it will donate a proton to ammonia, ammonia accepting a proton or a hydrogen ion, and it forms ammonium ion. When water loses a proton, it forms OH. This OH can take back a proton from ammonium ion to form again water. So in this case, we have water as the acid with its conjugate base OH. It's a base because it has the capacity to accept a proton. Ammonia is a base because it has the capacity to accept a proton. When it accepts a proton, it forms ammonium ion, which is a conjugate acid. This has the capacity to release the gained hydrogen ion, and that's why it becomes an acid. So, what is the end principle? When an acid donates a proton, it forms a conjugate base. And when a base accepts a proton, it forms a conjugate acid. Meaning, the acid will always exist with its conjugate base, and even a base will always exist with its conjugate acid. I pause. Take a close look. Take a minute and comprehend the meaning of the acid-base conjugate pair. Take a minute, look at those structures, and comprehend what do we mean. We're talking in terms of losing a proton, gaining a proton. When you lose, you become an acid. When you gain, you become a base. Meaning, water lost, OH is formed. OH can also gain a proton, and so that's why it is becoming a base. But it's a conjugate base for water as an acid. Finally, these are the acid conjugate base pairs that you can come up with. This is an acid, this is a base. This is an acid, this is a base. This is an acid, this is a base. So in solution, an acid will always exist with its conjugate base. I think the aspect of conjugate base, acid-base conjugate pairs is done. Now, let's look at the third definition, Lewis definition. Lewis definition. So, to him, after about 7 years, when the Bronsted-Lowry had stated their theory, he also came up because he found some things which are tricky. For instance, he said, okay, he noticed that when you bring in hydrogen ion in water, the water donates a pair of electrons to form hydronium ion. So to him, he said, an acid should accept a pair of electrons. In other words, a hydrogen ion will be an acid if it is in solution because it can accept a pair of electrons from oxygen in water. In the same way, a base should donate a pair of electrons to form a dative bond. So when you look at water, if you recall, we've been using water as an acid or water as a base. It will become a base because it can donate a pair of electrons. Hydrogen ion from HCl, for instance, will become an acid because it has accepted a pair of electrons. So, to them, if you summarize, you'll find that it's all about hydrogen ions in solution, and the solution becoming water. We shall come to that summary later on. So, from the Bronsted-Lowry definition, here comes the categories of acids. So acids are categorized into two basing on the number of moles of hydrogen ions they release in solution and whether they ionize strongly or weakly. That is the degree of ionization. Looking at the number of hydrogen ions they release in solution, you can have monoprotic acids or diprotic acids. Monoprotic acids, we have HCl or hydrochloric acid or nitric acid, or ethanoic acid, which is found in lemon, which we call acetic acid. They are all monoprotic acid, or lactic acid, which is in echivugutol. It is also monoprotic because it releases only 1 mole of hydrogen ions per acid. Then if it can release 2 moles of hydrogen ions from that single molecule of the acid, then it becomes diprotic acid. I think this is clear. Mono meaning 1, di meaning 2. And if it releases 3, it becomes triprotic acid. If it releases as many, then that's where we have the word polyprotic acid. That is depending on the moles of hydrogen ions released or denoted. When it comes to the strength, we have weak acids and strong acids, and this is what has been very, very common. If we look at strong acids, we look at the degree of ionization. If all the molecules you have for acids break down releasing hydrogen ions, then that is called a strong acid. An example is hydrochloric acid. There is 100% ionization. All these molecules, 1, 2, 3, 4, have completely broken down, releasing hydrogen ions. And on the other hand, weak acids partially ionize. Example, the acetic acid in the lemon. It's a weaker acid. That's why even when you feel that sour taste, it's not as strong like if you took like sulfuric acid, which we normally know to be corrosive to our body. So lactic acid, or what we call, ethanoic acid, or what we call acetic acid, partially ionizes. The amount of the mole of the acid that has ionized are very low compared to unionized molecules. If we look at this, you have about 10 molecules, 1, 2, 3, up to 10. Only 1 has broken down, releasing hydrogen ions. So this becomes a weaker acid. An example here is this acetic acid in lemon. So a quick aspect to look at is for weak acids, you will always have unionized molecules. Then you will always have unionized molecules and ionized or dissociated ions in solution. That is a quick difference. I think it is clear in here. So the question is to know, how do I know it is a strong acid and how do I know it is a weak acid? It's all experimentally obtained. We shall look at this when we come to the quantitative part of ionic equilibrium in Form 6. So, strong and weak bases. Remember, an alkali is an alkali if it releases OH ions or if it is soluble. So basing on that, you can have strong alkalis which also ionize completely, like sodium hydroxide, or a weak which ionizes partially, like ammonia. It's about the amount of ions that are in solution. If you look at this, only 1 ionized, others remained unionized. Here, everything ionized. That is the whole aspect to look at. Summary. Let's summarize up the lesson. Definitions, that is the crucial part. Depending on who is defining, Oswald says simply release hydrogen ions, a base simply release OH ions. Bronsted says you must donate hydrogen ions to a base, and the base must accept the hydrogen ion for it to be a base. Lewis comes and says it's simply an electron acceptor. Hydrogen ion accepts electrons. Or a base is electron donor. Water donates a pair of electrons. So what is the overall summary? The summary is an acid is an acid provided it has hydrogen ions. I think that is very clear. You see what is very, very common in here? Hydrogen ion, hydrogen ion, hydrogen ion. Alkalis, they should have OH. You see what is common here? OH, OH here, and OH here. Irrespective of what you define or how you state it, those are the unique factors. And that ends up with our acids and bases. Now you know what is a strong base and a strong acid. You know all the definitions of the acids and what is the general summary for the acids. And you know whether the acid is monoprotic or diprotic or polyprotic. And as usual, I leave you with an exercise. That is exercise. It is not named exercise 1 or 2 because it is for the single unit. Please go through it and answer the way it is asking. Like number 2 is asking you to illustrate using structures of ammonia, water, and NH4+ for you to identify which species is a Lewis acid and which one is a Lewis base. Meaning, you need to understand what is a Lewis acid and what is a Lewis base, then look at the structures, know which one is going to donate and which one is going to accept electrons, then you can identify the correct answer. That is a high-level understanding. I hope you will follow it up and get the answers. Thanks for being part of the lesson. Again, I'm still happy and enthusiastic to be interacting with you. I want to see you in the next unit. Please stay safe, follow the Ministry of Health regulations, and take care of yourselves. Alan is my name. Bye.